Okay, so, yeah, so this is what we call an existence theorem, because it doesn't really do anything in terms of finding a value that we're talking about. That leaves that up to you. But it just proves the existence of the value that you have to then go find, okay? So why are these useful? Well, they're useful as kind of a check to see if you need to go look for the value in a way. Okay, so what this says, let's make sense of this, piece by piece. Let's read through it once and then we'll take it piece by piece. I don't know if I wrote this in the exact language of the book, but same idea. If f of x is continuous on the closed interval, meaning what? Includes the endpoints, right, on the closed interval from A to B, and K is between f of A and f of B, then there exists at least one number C on the open interval from A to B, such that f of C equals K. Okay, what's that mean? So let's take this piece by piece. If f of x is continuous on the closed interval from A to B, maybe we'll draw a picture. This is also what I would call a picture theorem. We have a lot of these, where you can draw a picture that really represents the whole idea of the theorem. So let's draw the picture as we go. So first part. Okay, so we got x equals A, x equals B. And I've got some function that's continuous on that interval, right? So I can draw without picking my pen off the board. Meets all the criteria that we've discussed about continuity, right? And K is between f of A and f of B. Okay, let me draw this. Let me go back and kind of redraw this just a little bit here. Let's go something like that. How about? So then, would you agree that's f of A and that's f of B? Okay, so K is just going to be some number you pick between f of A and f of B. Let's just call this K right there. How about? Okay. Once again, that's a pretty bad K. I think it's. I need a new pen. This pen is. It just doesn't.
How much are those pens?
I don't know.
What are they called? Like just Promethean board pen?
I would call it a Promethean board pen. So there exists at least one. K is between f of A and f of B. Then there must exist at least one number C on the interval from A to B, the open interval, right? So not including the endpoints, such that f of C equals K. Well, maybe we can illustrate this by just drawing the horizontal line y equals K. So where's the point in this case? Right there. That is a value of C. If I had drawn the line lower, we would have had in this case 3 places, right? Everybody see that? Okay, does that just strike you as being like kind of a duh expression? I mean, it just makes sense, right? How could you conceivably, if you're drawing a function, is there any way that you could start at this point and end at this point, drawing a continuous function that doesn't violate the vertical line test? Is there any way you could do that and not pass through every intermediate value at least once?
If the function dipped below f of A. Or
Well, okay, look. I challenge you to try it.
wait, so is f of A is the minimum?
There's
that
f
the
of
minimum
A
of
and
the
there's,
function?
and it wouldn't make any difference if it's a minimum or a maximum, but let's just, given this one, you're saying, what if you do something like this, right? But it doesn't make, I still have to get up to f of B. I'm still gonna have a different value of C.
Well, yeah, but is f of A, is that at the point A, comma, whatever? Like, is it at the starting point, or is it
Yeah.
just at the bottom?
Yeah,
it's
yeah,
at the
so we're just
starting
saying we've got some function, and when x equals A, we get some value of the function. When x equals B, we get some value of the function. There is no path you could ever draw that's a continuous function between the left and the right points that doesn't pass through every intermediate value. See what I'm saying? What's a physical manifestation of this? If we travel from Hermiston, from here to Hermiston, and it takes us half an hour to get there, and it's 30 miles away, right? Is it possible? So our average velocity is, let's say we do this though. Let's say we go, let's do something a little different. So we're gonna start here on the freeway at rest, and when we pass by Hermiston, the sign, let's say we're going 65 miles an hour. Is it possible that we never went 50 miles an hour? No. By the intermediate value theorem, it's impossible, right? Think about that, because our velocity graph, if we were to graph our speed, let's say our speed graph, has to be continuous, right? Our car has mass. We're getting into a little physics here, but our car has mass, so it cannot instantaneously move from one velocity to another higher velocity without traveling through all the intervening velocities. It's got mass. That would require infinite acceleration, and we can't do that because physics gods say you can't. It's got mass, right? We're limited. So we know then that the velocity function between time A and time B, here in Hermiston, is continuous, right? We have to, we can't just, does that make sense? I can't make a jump in velocities. And so f of a in this case, our initial velocity is 0, our final velocity is 65, right? And so k, if we say k is 50, that's a value between those functional values. And so this intermediate value theorem says, no, it's impossible. You have to go through every intermediate value at least once, right? Make sense?
I mean, realistically, this sounds really simple, but I feel like you're gonna throw a curveball at us.
No, I'm really not. This
Okay.
is, there's really nothing, this is not a big deal. This is, it's an important theorem in a way, because these existence theorems, they give us a starting place later in math. We can say, well, by the intermediate value theorem, it guarantees there is a value, and so we don't have to prove that every time, right? Okay. We just meet these criteria, then we know we have to have some intermediate value there, right? Yeah, there's an existence, proves the existence of that. Maybe we have to go find it though, right? So let's look at real quick, let's look at kind of an example of the kind of problem that you might see in the book here. So something like, how about something like this? What if we, go to problem 79. Everybody's got a book, so I won't write it down. Let's write down the function. So we want to do two things here. First of all, we want to see if this stuff that I've written down meets the criteria of the intermediate value theorem. If it does, we need to go find all of the values of C that make this true, okay? So what do we got here? We've got some function. Everybody agree this function is going to be continuous on the interval? Okay, where would it not be continuous? I mean, it is, but what kind of thing how do we know it is continuous? What do we not see there that would cause it to be discontinuous?
Denominator.
Okay, yeah, there's no x in the denominator, so we can't ever get a value of x that's going to force us to divide by 0. Check that one off.
There's no root.
There's no even roots, right? So check that off. It's not written as some bizarre piecewise function, right, where we've got different pieces that might not match up. So it's pretty innocuous, right? This is one that's going to be fine. So check, it's continuous on the interval, on the closed interval from x equals 0 to x equals 5. Okay, now what does this mean up here though? Explain this to me. That's important. Okay, that's the k value, right? So there's some, we're gonna show that there's some value of the function, and we'll just call the place where it happens c. Is there some place where the function must equal 11 by the intermediate value theorem? How would we find out? How do we know if this meets the criteria of the intermediate value theorem? It's continuous, check.
If you, 11 into, if you, have the function equal to 11, then you solve for x.
Okay,
Minus
but
c.
we still don't know if maybe we're on a snipe hunt here. I mean, maybe this is not gonna work. I mean, maybe this doesn't meet the criteria of the intermediate value theorem, in which case we might as well not even try.
Check the maximum.
Ah, exactly. We just wanna check f of A and f of B. So this is A, and that's B, right? So what's the value of f of A? F of 0 is -1. F of 5
29.
is, what is it, 29?
Yeah.
So is 11 between the value of the function at the endpoints? Values of the function? It is, isn't it? 11 falls in between -1 and 29, so we do meet the criteria of the intermediate value theorem. And so that guarantees the existence of at least one value of c where this happens. How do we find it? It's really non-calculus stuff.
You just, set the function equal to 11.
Yeah, set the function equal to 11 and solve, right? So then we know it's there. Now we could just go ahead and take our function and set it equal to 11 and solve for x. Right? Good practice. How would we solve that?
Add 1. Factor.
Okay, but before, I can't factor it yet. What do I have to do first? Good, I've got to put it in standard form. I've got to set it equal to 0. Right? It's got to equal 0, so when I factor it, I can apply the zero product property, right? So subtract 11, x squared plus x minus 12 equals 0. You see what I'm saying? Now we want to be able to say, okay, if we can factor this, then the product of the factors equals 0 only when individual factors are 0, right? Tricky. So how does this factor?
X is positive, plus 1.
So what are my solutions?
1 positive 3.
Okay, so which of those apply then? 3, not 4, because it's outside of the interval. Okay, make sense? Okay. What about, could we do something like this? Look at 83. I love this problem.
Words don't like.
No, it's good, it's good. Use the intermediate value theorem to show that for all spheres with radii in the interval 0 to 5 closed, there is one with a volume of 275 cubic centimeters. Okay. How could we do that? How could we prove that if we look at all of the infinite spheres with radii on the closed interval from 0 to 5?
If you have the formula for the volume of a sphere
Okay, what is that?
is,
Don't look it up. No.
come on,
You got, only way you can start to internalize these is if you force yourself to remember, recall.
the 2r2d2, right?
2r2d2.
2r squared d squared.
No,
No? Okay.
it's a volume. A sphere is only dependent on one parameter. What's that? So the radius must be cubed, right? There we go. 4/3 pi r cubed.
Yeah.
Okay, that's the
I
volume.
had Thompson for geometry,
No
so.
idea.
So that's V of R, right? Okay. And so then, what do we simply have to do here?
So the
Check A and B.
intervals,
Yeah.
yes.
V of 0 is 0, V of 5 is big, right? Everybody agree? I mean, 5 cubed is 125, I'm only multiplying by factors bigger than 1, right? And we're supposed to show, there is one with, yes, we do actually have to do the math. So, but we don't have to do much, I mean, we can show this pretty easily, so 125, even 125 by 1, even if we assume 4/3, we're conservative and said that's just 1 times pi, if we round down to 3, I mean, we're still gonna, this is gonna be a lot bigger, isn't it? We're gonna get something bigger than 375 minimum, right? So we know that, we can just say that. So we don't have to actually do any math. And then 2, whatever it was, 2 something is in the middle, right? And so we meet the criteria, because wouldn't you agree that the volume function is certainly continuous on that interval, right? There's nothing, nothing up my sleeve here, right? It's just pretty straightforward. And the value of k, or v of c, or whatever you want to call it, is between the values of the function at the endpoints. And so guaranteed, there is going to be a sphere with volume 275, or whatever the number was. Okay? Make sense? All right. There's a really good one. I hope I assigned it. 86. If it's not assigned, I want you to look at that one and just think about it and figure it out. It's good exercise, good thinking. Okay, so now I want to move on a little bit though. So this is not a hard section, it really isn't at all. This really just adds some things that we probably could already do, but it formalizes them. So what this talks about is limits that deal with infinity. So I'm just going to call it infinite limits. Infinity is really cool. Infinity is something, sometime we'll take a day, kind of a rest day, and we'll just talk about infinity a little bit. Infinity is, I could teach you guys a class that lasted all year that dealt with nothing except just infinity, just treating infinity.
How long would it last?
It'd be infinitely long. It would never end. But it's a complicated thing. I mean, if you go into college and study kind of math theory, this is where you'll deal with the concept of how do you treat infinities. Because infinities, what's really bizarre about this is you can have subsets of infinity that are also infinite. And then so how do you go through the whole process of making relative comparisons? Because that's important to do. We'll do some of that in calculus this year, just by virtue of the kinds of problems we do.
Which infinities are bigger?
Yeah. Mm-hmm. Yeah, and some infinities are bigger than others.
Right.
That's the truth.
That is.
Okay. So I'm going to start this off with something. We'll look at a practical example. Let's take the function f of x equals 1 over x minus 1 squared. Okay? So if I want to, for example, take a limit of this, right? So if we want to take the limit of f of x as x approaches 1, well, what do we get? What do we get? 1 over 0, what's that tell us? Well, yeah, we just say no limit, right? And what kind of a feature on a graph is that going to be then? If we have a 0 of the denominator but not the numerator, that's a vertical asymptote, right? So we get no limit. And we do know at least at this point that it's a vertical asymptote, right? But that's not very useful. Okay, knowing it's a vertical asymptote, the function could look very, very different and still have the same vertical asymptote, right? Let's go one step further with this. Let's say something like, what's the limit of 1 over x minus 1 as x approaches 1 from the left? Now, what's that going to give us? You might say it gives us 1 over 0, but we can do better than that. Sure, it's a 0, but I want you to tell me what kind of 0 are we getting here? Because we never actually get to 1, do we? Right? So we just know that the value of the bottom approaches 0, right? Doesn't actually get there. Agreed?
Zero.
So if we're taking a value slightly less than 1 and subtracting 1 from it, what can you tell me about that very small number that approaches 0? It's negative, okay? So this is my own notation. This is not in the book, but I think that makes a lot of sense. Okay, we'll call that a 0 minus. And what does that imply? It's approaching 0, but it is negative. Okay, so now we can do something about this. That tells us if I take a positive number divided by a vanishingly small negative number, what is the result?
Big old number.
Okay, but
Big old
without
negative
limit,
number.
right? So what am I gonna write here? I'm gonna write infinity, right? But what flavor? Is it positive or negative? It's negative, because our definition of the sign of a quotient is that a positive divided by a negative is negative. You get that? That's useful. That tells us something important. That tells us that when the ant approaches 1 from the left, the function is plunging down to negative infinity. Okay, that's good. Let's do the same thing now. Let's approach from the right. The limit of 1 over x minus 1 squared as x, oh, hang on a second though. Whoops, I forgot the squared. We gotta go back for a second.
So now it's just a bigger infinity? Oh.
No, we don't have
It's
to
a
worry
smaller
about,
infinity.
but that's really irrelevant because there's no limit on how close we get to 1, but it does impact the sign, doesn't it? Right? Because what I've really got here is 1 over 0 minus squared. So you tell me, what is 0 minus squared? 0 plus, right? It's a vanishingly small number. Squared is still vanishingly small, but a negative times a negative is positive, right? So this works out to be 1 over 0 plus, which is positive infinity, right? Okay, what about down here? Same thing, if we take the limit as x approaches 1 from the right, well, I'm gonna get 1 over, what's the number inside gonna be? If I take a number slightly bigger than 1 and subtract 1, what do I get? 0. 0 plus. I get a small positive number, right? And so that's equal to 1 over 0 plus, and so that equals positive infinity. But that's pretty useful because that gives us some real insight into what this graph looks like now. We know that we've got a vertical asymptote at 1, but this tells us that our function is approaching positive infinity as we approach from both sides. So it looks like that, right? Make sense? Okay, how about, okay, so try, just, we'll warm up. Try this one on your own real quick. Try, okay, so take some limits that are gonna help us graph this function. We're gonna start to think about, this is earlier than I've ever done this, but we'll talk about it. We're gonna start to think about how we could sketch this curve, because that's one of our goals as we move through calculus. That's one of our big goals, is that we're gonna learn how to sketch graphs using calculus.
Would it be incorrect to write this problem like just initially when you're figuring out what points or what limits you want to find to be able to sketch it, to just list like x approaches to positive or from the right, and then just right below that x approaches to
Yeah,
the left?
so those are the limits you're gonna take, aren't they?
Yeah.
right? Those are the interesting limits, and we know that because if I gave you this function and I said identify all of the discontinuities in the function, you've already done stuff like that, right? The discontinuities are gonna be, in this case, where the bottom is 0, right, and the top is not. And you could all identify that's at 2, right? So we wanna take the limits as x approaches 2 from either side to give us an idea of what's it doing. Because it's got two possibilities. If it's a vertical asymptote, either it's going up or it's going down along the asymptote, right? Okay, so do that. Do that. We want to be able to fill in the blanks here. I want to be able to us to be able to provide a fairly reliable sketch of what that graph looks like. All right, so we're going to take the limit here. Whoops. We're going to take the limit of f of x as x approaches to, John, which one do you want to do?
Negative.
Negative. Okay, so we approach 2 from the left. What's that going to give us?
Positive.
1 over 2 minus 2 minus is what? 0 plus, okay. Everybody agree? Okay. So then our answer is, how do we interpret this? Well, we know we've got a constant on the top and a 0 on the bottom, so we know it's infinite. We look at the signs, positive over positive is positive, right? So we know we've got an asymptote at 2, and as we approach from the left, we know it's going up to infinity, right? Okay, so there's another issue here that we'll talk about later, and that is what's the end behavior of the function. We're not really there yet, but could we find maybe one key point that might be useful to us on this side? What, I mean, we know that it's gonna do this kind of a thing, right? Is there a point where we could sort of anchor our sketch a little bit? It's a minor issue, but well, there's one in particular that might be pretty good. I mean, we could find one, right? We could just plug in an x value. But why not plug in an x value of like 0, right, to find the y-intercept? See what I'm saying? Because that y-intercept occurs where x equals. So if I plug in 0, what do I get? 1/2. Okay, so we know it's going to go through that. It's going to go through that point, and it's got to be asymptotic. So it's probably doing something like that-ish, right? Okay, what about the other side then? Let's see what we got on the other side. Let's take the limit of f of x as x approaches what? Wait a minute, what are we gonna do? 2 plus. What's that give us? 1 over
Negative 0.
over 0 minus, right? And so that's gonna be what, negative infinity? So that tells us on the other side then that we're going down to infinity. Well, we might think, okay, let's try to find a place where it crosses the x-axis. So I could set this whole thing equal to 0, right? Does that make sense? Set y equal to 0? Yep.
Yeah.
Did you hit it, Cory?
Oh.
I did. Yeah, thank you though. I didn't know for a second if I did myself. So if I set that equal to 0, how do I solve that?
Multiply it by 2.
So what would I do? I can't.
Just do a different point.
Yeah, I mean, I
Like,
could.
If
You're right.
yeah,
I
if I were
could.
to do it.
I'm not going to find. That's not going to work, is it? Right? There's no solutions to that, are there? I can't cross multiply. In fact, if you think about this, what is the behavior of x going to have to be to make this thing equal 0? to make this thing equal, I can't make it equal 0, because the only way you get a fraction to equal 0 is when, which part equals 0? The numerator, right? Numerator is fixed at 1. So there are no solutions. The only way I could make this happen is if I let
Wait,
x get super huge
Couldn't
and
you-
just approach infinity. But what that's telling us is that it's never gonna happen. It'll get close to it way out there, right?
Couldn't you multiply both sides by 2 minus x?
Well, sure I could, but then I'm gonna get, what's that gonna give me? I'm gonna get 2, I mean, what do I get there?
Then you get 2 minus x equals 0.
Oh, okay, but I've multiplied both sides by a factor of x, and so I've introduced extraneous solutions, and so your solution is going to be extraneous. And to prove it, we could go back and check it to see if it worked, and it won't work. Okay? Not a good idea, but it's just not, it's strictly verboten. So we might pick a different point. Maybe we'll pick something like, how about if we picked x equals 4? If I plug in 4, I'm gonna get negative 1/2. Looks kind of symmetrical, doesn't it? So there's a point right there. And it's going to negative infinity, so how about that? Looks like it's sort of symmetrical about a certain point, but we'll get there later. Okay? All right, good stuff. So how much time we got?
4, 5, 6 minutes.
6 minutes.
It's
Okay.
nonstop.
Just
No,
to
it does not.
interrupt to yell at Hillary.
And
Okay, let's last issue then. Let's just try something like this. How about? It's good stuff to do, huh? Oh, I like this. So good. Good. Yeah, let's do this one. Okay, I want you to do some stuff with this. I want you to find and characterize all of the discontinuities. And then we're going to take it one step further. In the vertical asymptotes, we want to know what's happening at the vertical asymptotes. And then maybe we can turn that into a sketch. Okay. Is anybody able to rewrite that in a way that's probably helpful?
you can back to the bottom, x plus 2, x minus 6.
Okay, so bottom in factored form is x plus 2, x minus 2. What about the top? Okay, so then somebody tell me, where is a hole?
Plus negative 2,
Where? No.
x minus 2.
Where, at what value of x do we have a hole in the function? Positive 2 is correct. How come?
Because the top equals 0.
Okay, good, because the limit of the function as x approaches positive 2 is 0 over 0, right? So we've got these holes in the function, we've got these factors that both go to 0, right? I could fill in the hole by just canceling those out and using this function instead, right? So one thing we know is we've got a hole at x equals 2. Are there any vertical asymptotes?
No, just think.
Just negative 2. Negative 2 is special. How come at negative 2?
Because when you do the thing, it only does negative 2.
Okay, if I evaluate, or if I evaluate the limit of the function as x approaches negative 2, I get the result a number divided by 0, right? Which means vertical asymptote. Okay? Right, does that make sense?
Yeah.
So rule of thumb, a value of x that produces zeros top and bottom as a whole, a value of x that produces a zero on the bottom but not the top is a vertical asymptote. A value of x that produces a zero on top but not the bottom is what? A zero. Yeah, because 0 divided by a number is 0, right? So we have a vertical asymptote at x equals -2. And then this is kind of just incidental, it's just an anchor point for us. But we actually have a 0 at x equals what? -4. No, not 2. 2's a whole.
Oh, yeah, because it's 2.
At -4, right? So that gives us the bones of our sketch right there, right? We know the vertical asymptote is key. That's the one that's a big feature of our graph is that vertical asymptote. Now we know we've got a 0 at -4, so that helps a little bit, right? What about a y-intercept? Could we find a place where there's a y-intercept? If I set x equal to 0, what do I get? That just means, using the cover-up method, then yeah, so it's just gonna be +2, right? Everything with an x goes to 0, leaving us with -8 over -4, right? And so we get a point there, so we got some points to anchor this. Now though, and we have a hole, we said, at +2.
We don't know where.
Well, we don't know where, but we could, if we took the limit of the function as x approached +2, we could get it. I'm not gonna go, we don't have much time. That just means we're gonna cancel, we're gonna fill in the hole, right?
Yeah.
To find the limit. So now as x approaches +2, what do we get?
So, 3 seconds?
Yeah, 6/4, so
Yeah.
3/2. So we'd know that at x equals 2, there's gonna be a hole right there, okay? But there's one other feature that we need to know. We need to know, what is this thing doing at the asymptote, right? So that's the stuff we talked about today. There's our infinite limit.
Alright,
Oh, gosh.
that was close.
Yeah, we were close.
Almost was a piece of butter. Yep.